Hi, we're going to be talking about subspaces, and the key task we're going to need to be able to do is to find a basis for the null space and find a basis or spanning set for the column space. What is a subspace? Well, it has three properties. So a subspace must have the zero vector, okay? Must be closed under addition. So if I have U and V and they're both in the subspace, then their sum must also be in the subspace. And we also have closure under scalar multiplication. So if I have a vector V that's in the subspace and I multiply it by any real number, then the scalar multiple of the vector V is also in the subspace. Now, we've actually just been referring to these subspaces as the span of a set of vectors, right? So if we have a basis and then just whatever those vectors in the basis span, that's the subspace. So what we need to do in MATLAB is find a basis for the null space and a basis for the subspace, the column space, sorry. So first thing I'm going to do is I'm going to do RREF of A, and I'm going to find out where the pivots are. Now this is interesting. So notice that we have three pivots all along the main diagonal here. What does this mean? It means that the first three vectors are linearly independent. When I take them as a set, these three vectors are linearly independent. So just these vectors themselves, the original vectors, will form a basis for the column space, right? So if I want to find the column space of A, has a basis, right? And of these vectors. And I'm going to type them in and pause the video while I do it. So this is all the task is. We just identify the pivots in the matrix, and then the columns of A, treated as vectors, will form a basis for the column space. So my first basis vector is 0, 2, 0. My second basis vector is 2, negative 5, 1, and then negative 5, 2, positive 5 is my third basis vector. Okay, so that's fairly straightforward. What about the null space? Okay, well, we're still going to use the reduced row echelon form, but now remember the null space is the solution, all possible solutions to the matrix equation A times the vector x equals the zero vector. So the null space is any vector x such that when I multiply it by A, I get the zero vector. And of course, the zero vector is always in there. We know that. So what I want to do, though, is I want to augment the zero vector with the matrix A. So I need a 3 by 1 matrix to augment. So notice what happens. The reduced row echelon form is the same. It's just tacked on the zero vector. And so now what I do is I just solve for the, I just find the solution set in vector form, and those vectors will be and I'll have one vector per free variable, so that vector will be the basis for the null space. So just solving this, right, we can see that my x sub 1, when I move the 11 over to the other side of the equation, right, I have x sub 1 equals 11x sub 4. And then x sub 2 equals 9x sub 4. And x sub 3 equals 2x sub 4. So we're just doing some basic math, all right? And so what this means is that we have a vector that's of the form, right? We have a solution vector which is of the form, right? I need an 11, oops, sorry. I need an 11, and then a 9, and then a 2, and then a 1. Sorry, I didn't have a semicolon in between the 2 and the 1. Okay, so that's going to be my basis vector. Why? Well, because every solution to the homogeneous equation has to have this form. And the only way for it to have that form is to have this vector, right, times the real number x sub 4. So then the vector 11, 9, 2, 1, that can serve as the basis for the null space. So that's not too difficult, right? Let's look at this. Now we're looking at matrix B. So I have a slightly different matrix going on. We have a 4 by 5 matrix. And let's look at its reduced row echelon form and notice the pivot columns. Okay, so any column that corresponds to a pivot is a linearly independent vector. And so the basis for the column space is going to be these 4 vectors, the vectors corresponding to the pivots. All right, so again, I'm going to pause and write these in the equation editor so you can see the solution. So the solution here is the 4 vectors. We have these two, right? V1, and I've called them V1 and V2. And then these two, because they correspond to the pivot columns. And I've skipped 3 for the obvious reason that I'm talking about the 4th column and the 5th column here. So that's the basis for the column space. So too easy. When we're finding the basis for the column space, just do REF or RREF of the matrix, find out which the pivot columns are, return to the original matrix to get the original vectors, but then those original vectors that correspond to pivot columns will form a basis for your column space. And for a basis for the null space, we need to, again, get the 0 vector appended here. So we're going to do zeros. It's a 4 by 1 vector that we need. Let me close the, that'll augment the matrix B with the 0 vector. And again, you can see the 0 vector here. And so now all we need is to have, well, to solve for, figure out what the form of this solution looks like, right? And we know that x sub 4 is going to equal 0. And we know that x sub 3 is also going to equal 0. And then x sub 2 is free. Wait, I'm sorry, I was off by 1. This is x sub 5 is 0, x sub 4 is 0, x sub 3 is free, x sub 2 is equal to minus 1/2 of the free variable x sub 3, and x sub 1 is equal to x sub 3, right? When I subtract the minus 1 over to the other side, sorry, that's an equal. Okay? Which means what? Which means we have vectors of the form. So my vector x has to be of the form 1 minus 0.5. I'll just use 0.5 there. 1, 0, and 0. Right, so I just make sure that the vector I choose, right, has all of these properties, right? So x sub 4 and x sub 5 have to be 0 because of this, right? And that's correct right there. And because of this, x sub 2 has to be equal to minus 1/2 x sub 3, which is going to happen right there. And of course, x sub 1 and x sub 3 will be the same, so they'll both be 1s. And when I put all of that together, then we know that all possible solutions look like what? Well, all possible solutions look like this vector times the free times, well, yeah, the free variable x sub 3, and the free variable can take on any real number. So since the free variable x sub 3 is just some real number, any scalar multiple of this vector is a solution to the homogeneous equation. set of homogeneous equations, which means that this vector is a basis for the null space. So it's pretty straightforward in this chapter. For the null space, we are going to have to solve the homogeneous equations and put the solution in vector form and grab those vectors that correspond to the free variables. And for the column space, it's much easier. We just determine the pivot columns and take those columns from the original matrix to be the basis vectors for the column space.